I take two markers here, and we'll get different colors so they stand out a little bit more. I'm going to knock these two markers off the table, and I'm going to do it at the same time. The way I'm going to do it is I'm going to take a ruler, put it together, take a ruler, and then I'm going to sort of sling it like that, so that the black marker is going faster than the orange marker. So the rhythmically shot out, black marker traveling faster than orange marker. Black marker, obviously, since it's traveling faster, will travel in an arc. I guess officially they both travel in an arc, but the red one, not much of one. So the black one is going to do a maneuver something like that. The orange one is going to do something like that. Hopefully getting the same ground. So the question is, which one is going to hit the ground first? Physics by democracy. If you don't know, just take a blind guess.
The orange one.
Okay, we'll start with the orange one. Who says the orange one's going to hit first? Who says the black one will hit first? That booked. Is that a commitment? Yep. So I got two. And who says a tie?
Wait, you said tie?
Pardon?
Did you say tie?
Tie, yes. We got 1, 2, 3, 4. And who says they will burst from the flames all the way down? I'm assuming the people who did not vote that time. All right. Tatum, you're going to probably have the best viewpoint here. So if you don't think that Tatum's going to accurately represent what happens, feel free to move around so you can see it. Go a little bit higher so that they don't flip. Which one hit first? Orange hit first? What did you see, Mara?
I swear I saw both of them at the same time.
You said they both hit at the same time?
Mm-hmm.
You said?
Because I could let this happen.
Oh. Let's do that one again. Here we go.
I feel like the orange did hit first this time. Barely.
To me, it looked like I heard the sound at the same
That's
time.
what I'm saying.
Yeah.
I'm hearing it. It's not only what I'm seeing. I'm using my second senses.
They're supposed to hit at the same time. Now, if nothing else, if say one does hit before the other one does, because they didn't go off the table at the same time, I think black went considerably faster, but it didn't seem to make much of a difference at all in how fast it took to fall. What we're getting towards here is the fact that how fast they're going horizontally does not affect when they hit the ground. So if I want to figure out how fast they were going, I just need to figure out where does it hit the ground. If I know the initial height, I can calculate how much time it takes for it to fall. And once I know how much time it takes to fall, I can then figure out what that horizontal speed is. Because there's this independence between horizontal and vertical, we basically are doing what we did in chapter 2, except twice. So let's start out with the horizontal problem, and then we'll move to something more mathematically interesting, complex. And then, given enough time, we'll do the most complicated one. So if an object is being thrown horizontally off of a cliff, that is 50 meters tall. It is shot initially at 30 meters per second, and I want to know how far from the base of the cliff does it land. R for range. Now, what is the direction of acceleration once it's in the air? Eva?
Down by 9.8 meters.
Yes. Once it's in the air, the only force acting on it is the force of gravity. Nothing else is. We are, of course, ignoring air resistance. If you wish to bring air resistance into it, then good luck with those calculus problems. While it's in the air, the only force acting on it is the force of gravity, which is acting downwards, by definition of down. And so the direction of acceleration, the only way the velocity is going to change is down. So, generally it's recommended. When you're setting up your coordinate system, it is a two-dimensional problem. We need a sort of an I-hat and a J-hat. Although if you look at some of the videos, I just call it horizontal and vertical. I'm going to say I-hats to the right. It is helpful to have one of them in the direction of acceleration, or at least parallel or anti-parallel to the direction of acceleration, and the other one perpendicular to that, so I-hat's perpendicular to it. And then J-hat, up or down, it doesn't matter, be consistent whichever one you do. Anyone with an opinion?
Oh.
All right. So I'll have set of I-hat values. We have displacement, initial velocity, final velocity, acceleration, and time. And then we'll have a set of J-hat. We are trying to find this. So, what do we know?
We know the displacement is 50 meters.
Say that again?
We know the displacement is 50 meters.
For J hat.
All right,
Sorry, yeah.
sure, we'll go with that. Do we know anything else?
I have a quick question.
Yes.
If J hat is up
Uh-huh,
and it's going down, do we have to put like a negative?
yes.
Okay, then it's negative 50 meters.
Potentially, we would have caught that mistake in a moment. Or not. All right, what else do we do? We know 4 more pieces of information. Robin?
The 30 meters per second is going negative, and I think in the J. No. No, cause it's going that way, so it's then.
Yeah, it's I-hat. I-hat to the right. So this is 30 meters per second. We know 3 more pieces of information.
The acceleration is 9
Negative.
Alvin?
Negative.
Yep. Why is this negative?
Is it's going down when J hat's going up.
Why is J-hat going up?
Because we chose for it to do so.
Yeah, or specifically, I heard Ava tell me. And then she decided to switch in the middle of it by making this positive. This is what I mean by pick one and be consistent. If up is positive, then these have to be negative. And the reason I said that we might catch that other mistake earlier, when we made this positive, if you make this positive and that negative, then you would be asking you'd be trying to figure out at what point is this object 50 meters above where it started, which should have been never. So, but the big thing is these are the same sign. If you make them both positive, you're saying down is positive. If you make them both negative, you're saying up is positive. All right, we know 2 more pieces of information.
Initial velocity for J hat is 0 meters per second?
Yes. And
Is it, do we put a negative or something?
No,
No,
it's 0.
there's
That was positive.
I know.
Final velocity will be 0.
why?
Oh, because it's on the ground.
All right. Let's get the answer to my question first, and then I want to address that, because that is a common mistake.
Okay.
And I understand why students think that, but hopefully we'll dispel that.
Got it.
What's the other piece of information? Ash, you look like you have an inkling of something? Okay.
I hat acceleration is 0.
Yes. As I said, the acceleration is downwards, which means there's no horizontal. So 0 meters per second squared. If you want to make the 0 negative, have at it. Okay. Now, we're trying to figure out how from the bottom of the cliff does it land. So I understand you're picturing it landing, it's stopping when it hits. The physics language is how far from the bottom does it hit? What we're actually solving is how far from the bottom is it just before it touches the ground. Because as soon as it touches the ground, acceleration is no longer that, the acceleration changes. And so it's no longer a constant acceleration problem. And it's a far more difficult problem to deal with.
Why does the acceleration?
Because
Because-
it's stopping. Because it's hitting the ground and stopping.
Another force is being applied.
No force is being applied.
Another one.
As soon as it touches the ground, we have the force of gravity acting down, but now we have what's called a normal force acting up.
Acting up.
Maybe some friction too.
So that the net force would be different?
Yes. Now, I've got these different characteristics here. Final velocity, there's no reason for the final velocities to be the same. But time. Time is the one that binds them. Even when I try to think of quantum physics where there's a bunch of exceptions when you get into quantum physics, I cannot think of an exception where time would not be the same. So it is in the air moving horizontally for the same amount of time that it's in the air moving vertically. Because we're dealing just before it touches the ground. So we need to find time. How do we find time?
Isn't this a formula involving
Third formula.
50 and 30, and don't you just divide that?
Yeah.
No.
Third formula for J.
Yeah. So what we're going to do is we need to look at just either the J hat or the I hat. Now, you could look at it combining both. I do not think that is simpler, but if you insist, I can do that. However, let's solve J hat. The vertical establishes how long it's in the air, and the I hat establishes how far it will go. So, using just the J hat information, which equation would be used to find time?
The third formula.
All right, so I have delta S equals VIT plus 1/2 AT squared. Just J hat information. Negative 50 equals 0 times time plus 1/2 negative 9.8 time squared. So I have T squared is equal to negative 50 over negative 4.9. And so T ends up being 3.2.
Oh, no. 10.2.
What'd you get?
10.2.
That'd be T squared.
Oh, sorry. 3.19.
1.9?
Yeah.
Okay, not 2, just to make sure that I'm not right. Is that,
Yeah.
that what I hear? Okay. I should have taken it out farther.
Second.
Thank you. So I now have time 3.19 seconds, 3.19 seconds. Now I can find R. What equation do I use to find how far it went horizontally?
The third one.
Okay, it looked like you changed your mind halfway through that.
I just did it.
So this is the vertical. And now we'll bring in our j hat. Now we're gonna do the I hat. Same equation. I have R is equal to 30t plus 1/2 0 t squared. Oh, I know what t is. So R is 30 times 3.19. $90.57.
95.7.
Meters.
And that's the answer to the question. It's just what we were doing before, except we did it in 2 parts. Questions to here? Because you know my next version is going to be more difficult for us. All right, let's do it. I guess we'll keep the same basic structure up. Let's still solve for R. Still projectile motion problem on Earth. Let's Earth. Except this time, it's now being shot upwards. 30 meters per second, and let's make this a 37-degree angle. Now, I drew it as if this thing is going to be going farther. I don't know if it's going to go farther or not. There is some optimum angle at which it would go the maximum distance. And if they are not on the same level, it is not 45 degrees. But I don't know if 37 is optimal or not. I know if I shot it at 90-degree angle, it would go 0 from the end of the cliff. All right, so I still have acceleration the same as before. I'm sticking with I hat, j hat, both being to the right and up, unless somebody wants to object. All right, so what has changed here is my initial velocity. My initial velocity is no longer 30 meters per second I hat plus 0 meters per second j hat. I have now some horizontal and some vertical component. And this gets back into, I've given it to you in polar notation here. Well, close enough. If my initial velocity is 30 meters per second, 37 degrees, what is it in polar form? Try that one again. What is it in rectangular form? Where we're breaking it into horizontal and vertical components. This gets into the trig that we did at the very beginning. I have 30 meters per second, which I'm breaking up. I want to figure out how far to the right and how far up it is. That's a 37-degree angle. The question is, how do I find the lengths of those sides of the triangle?
Is rectangular form the same as trig notation? Or not?
Maybe trig, we use trig to solve it if it's in
Okay.
polar.
Okay, then it's probably that.
So the adjacent side, this is adjacent to 37 degrees, cosine or sine?
Cosine.
And if in doubt, alphabetical. Cosine, sine, x, y, adjacent, opposite, abscissa, ordinate, horizontal, vertical. This assumes that you're given the angle next to the horizontal, but works alphabetically all the way down the list. So this is the hypotenuse times the cosine of 37 degrees, and this would be the hypotenuse times the sine of 37 degrees. So this is about 24 meters per second, and this is about 18 meters per second. I think that's right, yeah, feel comfortable with that. Now, it's gonna be a little bit off, you can use a calculator, so there'll be some rounding here. There was a test where I actually gave the angle out to 10 decimal places, and then wrote somewhere that the cosine of that angle is 0.8, the sine of that angle is 0.6. Just so that the numbers work out nicely. And some people using the calculator just took that angle, rounded it off, and ended up with something that wasn't as nice. I guess that was their choice. So, over here now. My initial velocity, I hat, is 24 meters per second. And J hat, 18 meters per second.
You forgot the negative signs.
In which direction is it being shot initially?
Oh, I lied.
This is the point. In the last problem, as long as your displacement and acceleration had the same sign, you would get a correct answer. Here, though, velocity is a different answer, a different sign